it comes to developing ideas about how the brain relates to cognition, to our being in the world, it's easy to get distracted by the complexities of the affair. The brain is horrendously complex, and as we'll see, our methods don't really clear things up. They leave us with many, many puzzles. But we're going to look first now at two cases in which thinking about the brain has been prompted by relatively low-tech intervention. In one case, it's an old case, very well known in the historical record. This is the case of Phineas Gage. And the other will deal with a modern approach to treating phantom pain in amputees. So going back now all the way to 1848, we meet the character of Phineas Gage. Phineas Gage is very important in the literature because he suffered an accident which damaged his brain. And his was the first pathological case in which doctors came to recognize that selective damage to a part of the brain could lead to major changes in the psychology of the person, for lack of a better word. Now, Phineas Gage's case shares a property of all pathology cases, which is that they're completely unique and uncontrolled. Every injury is different from every other injury. And inferring from a broken brain anything about a working brain is going to be very, very difficult. This is a photograph that recently surfaced of Phineas Gage. He's carrying an item in his hand which is called a tamping iron. And you can see from the pictures here a graphic illustration of what happened. He was out working the railroad and they were drilling holes in rock, patting gunpowder down, tamping the gunpowder down, and then putting in a fuse. And it was during the tamping of the gunpowder with this tamping iron that a spark was generated, and it blew the tamping iron literally out of the ground and in through here and out the top of his head, and it landed somewhere behind him, blowing away most of the front left part of his brain. Absolutely horrible. Horrible incident. It's not clear whether he lost consciousness at the time. He did go home sick, as you would. There's the tamping iron in question. It's on display, I think, in Yale University. And the interesting thing about Phineas Gage is the difference between him before and after his accident. He's recovered remarkably well given the size of the injury he had done to himself. But his friends and colleagues were of the opinion that something drastic had changed in poor Phineas. He had beforehand been the kind of person you could rely on. He was, as they say, a capable and efficient foreman with a well-balanced mind. He was a smart businessman, and he was easy to get along with. But afterwards, he was very difficult to get along with. He was impatient, obstinate, and his friends generally said he was no longer the Gage that they knew. Now, this abrupt change in his diffuse personality went along with a very singular injury to his brain. And this was one of the first cases in which that link could be made between something as intangible as personality and a specific lesion in the brain. This prompted all kinds of thinking, and it led to all kinds of poorly informed work. It's not easy to draw consequences from a case like this. And as we saw with phrenology, there was a rush once more to rely too heavily on a psychological characteristic like personality and a place in the brain. Some of the excesses of the work that followed in the wake of Phineas Gage led up to the introduction in the 1920s and 30s of what was called psychosurgery, in which patients who were deemed to have very troubling mental illnesses underwent a medical procedure in which a needle more or less was inserted right here where the tamping iron had gone in with Phineas and moved around to turn the brain to mush. This is also known as a lobotomy. It's a most horrendous practice, and it went on until the 1950s. And it was directly inspired by simplistic thinking about the kind of change that we saw in Phineas Gage. There was a massive personality change after damage to the left front lobe. So you have someone with massive personality problems, so you damage their front lobe. That this is not sound thinking should be obvious. But you can see the direction of inquiry, and you can see why the Phineas Gage case was so notable. And it has led still today to wondering about these big frontal lobes we have, the most mysterious part of the brain, that part that in humans is freakishly large. We do have lots of questions about that, and people who like to attribute functions to brain parts often attribute such abstract notions as reason, control, deliberation, or personality to this part of the brain. But there's no secure way to draw those links. How many imaginative leaps do you have to go from a part of this organ to something like your feelings about yourself and who you are? So you can see here a very important case history that prompted people to think perhaps too physically about the brain and not critically about what they were trying to explain and what the brain actually is. But let's fast forward 150 years to a modern neuroscientist, V.S. Ramachandran, a most excellent neuroscientist who also took a low-tech approach to the brain, this time not with the crude intervention of a knitting needle. Ramachandran is a contemporary neuroscientist and well versed in everything that we know about the brain. But the way he thinks about the brain shows a great deal of intuition, which was sadly lacking in those who examined Phineas Gage. And to give you an example of the kind of intuition that someone who thinks well about these things can come up with, we want to discuss the case of phantom pain. Now, when you have a limb amputated, anyone who has a limb amputated ordinarily, almost always, has a residual problem after that with what's called phantom pain. The limb is no longer there, but it seems to the patient that the limb is there and that it hurts. And this is a very debilitating condition, and it's hard to understand. But we now know enough about the brain to begin to think in this area and to develop intuitions. So coming back to the brain itself, at the border between the frontal lobe and the parietal lobe, we find these two gyri. One is called the primary motor cortex and the other the primary somatosensory cortex. These two areas of the cortex have direct links to the extremities of the body. In the somatosensory cortex, we find direct connections to the receptors in the skin that give rise to touch. In the primary motor cortex, we find descending nerves that go out and will ultimately move the muscles. And we can discover through modern neuroscientific techniques that these connections, the wiring of these, is very principled and ordered. And we can associate specific parts on the skin or specific parts of the body with specific areas in these two parts of the brain. And when we do that, we can lay out these mappings. And here you can see the somatosensory cortex on the right in blue and the motor cortex on the left in red. And the mapping, shown here with body parts, of the parts of the body that they connect to. And what you see is that some areas of these parts of the brain have vast amounts of real estate given over to the hands and to the face and mouth. These are our most sensitive parts of the body, and they're also the parts of the body that we have greatest motor control over. So this is perhaps no big surprise. But this has been long known, since the 1940s at least. But there was a conception that the wiring in the brain is more or less fixed, that when these kinds of relations between parts of the brain and parts of the body are given, you're stuck with them. And the understanding of phantom pain was that, well, the brain hadn't been informed that the limb was gone, as it were. The brain was continuing to be active, including in those areas that had previously served the now missing limb. Now, Ramachandran produced a brilliant intervention here, which utterly changed the field, but he didn't do it using high-tech means. What he did was he saw that, hang on, it's as if this person is missing a limb and doesn't know they're missing a limb. There's a mismatch going on here. And he came up with a clever way to intervene in this situation, in which a patient who had an arm amputated sat in front of a box and looked at one hand, and then you place a mirror in the box so that where the other hand would be, which is gone, they now see a hand. Here's a mirror box in action. You can see that the lower hand is the real hand, the upper hand is a reflection of that hand, but the patient sitting there now sees two limbs, and this changes the game entirely. It proves to be an extremely effective way of dealing with phantom pain. And after a while, what we find is that mapping in the brain, which was appropriate for the body prior to the amputation, changes. It changes within a relatively short period of time. And one thing we learned from this is that the brain is far more plastic than we knew. And this also, for my money, is an example of a wonderful way of bringing intuitions about the body, what it is to live in a body, and thinking about the brain at the same time.